Assalamu alaikum. Let's begin lecture 27 of CS317 Operating Systems. This lecture also belongs to the topic of deadlocks. We are using chapter number 10 of the book by the author Gary Nutt. In the previous lecture, we covered more examples of the banker's algorithm. We realized that deadlock avoidance was still more expensive than detection and recovery. We explored reusable resource graph models. We learned how to detect deadlock for reusable resources. And we started the discussion on consumable resource graph models. The subtopic that we are going to talk about is deadlock detection and recovery. Let me remind you that we were working with consumable resource graphs. So, the first question is this consumable resource graph deadlocked? To answer this question, we attempt to reduce the given graph. Identify the blocked processes. P1 has 3 requests, one of which cannot be granted, so it is blocked. P0 is not blocked. Reducing the graph by P0. Being the producer of R1, P0 produces infinite instances of R1. The producer edge is removed. Infinity plus 2 is still infinity. That is why you see infinity inside R1. P1 has unblocked. Reducing the graph by P1. Remove the request edges, decrementing 3 instances of R1. Infinity minus 3 is infinity. Being the producer of R0, P1 produces infinite instances of R0 and the producer edge is removed. The graph has no edges. We say that the graph has been completely reduced. This shows that the initial consumable resource graph did not contain a deadlock and that it can be reduced using the sequence P0 and then P1. Is this consumable resource graph deadlocked? To answer this question, we attempt to reduce the given graph. Identify the blocked processes. P2 has a request which cannot be granted, so it is blocked. P3 has a request which cannot be granted, so it is blocked. P0 and P1 are not blocked. We choose to reduce the graph by P0. Remove the request edges, decrementing an instance each of R0 and R1. Being the producer of R2, P0 produces infinite instances of R2. The producer edge is removed. P2 has unblocked and P1 is now blocked. Reducing the graph by P2. Remove the request edge, decrementing an instance of R2. Infinity minus 1 is infinity. Being the producer of R1, P2 produces infinite instances of R1. The producer edge is removed. Both P1 and P3 are blocked. The graph is not reducible by any process. The given state is a deadlock and the participants of the deadlock are the processes P1 and P3 over resources R3 and R0. We came to this irreducible state when we started reduction with P0. Let us see the final state if we had started reduction with P1. Reducing the graph by P1. Remove the request edges, decrementing an instance each of R0 and R1. Being the producer of R3, P1 produces infinite instances of R3. The producer edge is removed. P3 has unblocked and P0 is now blocked. Reducing the graph by P3. Remove the request edge, decrementing an instance of R3. Infinity minus 1 is infinity. Being the producer of R0, P3 produces infinite instances of R0. The producer edge is removed. Both P0 and P2 are blocked. The graph is not reducible by any process. The given state is a deadlock, and the participants of the deadlock are the processes P0 and P2 over resources R2 and R1. We came to a deadlock whether we started reduction from P0 or P1. In both choices, the participants of the deadlock are different. Having talked about reusable resource graphs and consumable resource graphs, let's now talk about general resource systems. Real systems incorporate a combination of reusable and consumable resources. Deadlock detection strategies need to combine the consumable and reusable resource analysis techniques. The detection analysis is conducted by using reusable resource graph reductions on all reusable resources and consumable resource graph reductions on all consumable resources. For a state to be deadlock free, the reusable resources must be completely isolated by reductions. The consumable resource graph must have a sequence in which each process can be demonstrated to not be blocked on any consumable resource. Is this general resource graph deadlocked? R0 and R2 are reusable resources, while R1 is a consumable resource. P0, P1, P2, and P3 are processes in a general resource system which may use a consumable or a reusable resource. Identify the blocked processes. P0 has a request which cannot be granted, so it is blocked. P2 has two requests which cannot be granted, so it is blocked. P1 and P3 are not blocked. So we can choose to reduce the graph by either P1 or P3. Reducing the graph by P1. P1 releases all its allocated resources. Remember, R2 is a reusable resource. P2 has unblocked. Reducing the graph by P2. Convert the request edges to assignment edges. P2 releases all its allocated resources. Being the producer of R1, P2 produces infinite instances of R1. The producer edge is removed. No new process is unblocked by these actions. But remember, P3 has always been unblocked. Reducing the graph by P3. Remove the request edge, decrementing an instance of R1. P3 releases all its allocated resources. P0 has unblocked. Reducing the graph by P0. Convert the request edges to assignment edges. P naught releases all its allocated resources. Being the producer of R1, P naught produces infinite instances of R1. Infinity plus infinity is still infinity. The producer edge is removed. The graph has no edges. We say that the graph has been completely reduced. This shows that the initial general resource graph did not contain a deadlock. We can additionally understand that one consumable resource can have more than one producers. Here we have one consumable resource R1 and there are two producers for it, P0 and P2. And this given general resource graph can be reduced with the sequence P1, P2, P3 and P0. Note that both P1 and P3 were not blocked when we started, but we started reduction from P1. Let us now come to your homework. We have just seen that this general resource graph is not deadlocked, but the reduction sequence will differ if we start from a different process. Start reduction from P3. Furnish a reduction sequence. So far we have talked about deadlock detection. Now let's talk about the next step after detection, recovery of the system. Once deadlock has been detected in a system, the system will have to be recovered by changing it to a state in which there are no deadlocked processes. This means that one or more processes will have to be preempted, thus releasing their resources so that the other deadlocked processes can become unblocked. In some cases, the recovery mechanism may use the general resource graph to select processes to destroy. Checkpoint and rollback. When resources are preempted from a process, normally the process is destroyed. But sometimes we have a checkpoint or rollback mechanism in the system from which a process can be reconstructed. A process periodically takes a snapshot of its current state. This snapshot is called a checkpoint. The operating system saves the checkpoint for the process, and the process then continues its activity. If the operating system determines that a process is involved in a deadlock, it destroys the process, thereby releasing its resources for other processes to use. Next, it reestablishes the victim process state based on the checkpoint information and then restarts the process from the last checkpoint. This method is called rolling the process back to the checkpoint. Bringing the system back. After a process is destroyed, the deadlock detection algorithm is invoked again to see if the recovery was successful. If it was not, then another process is preempted. The recovery algorithm will eventually remove the deadlock processes, potentially by restarting all but one of the processes involved in the deadlock. Then the system continues normal operation. Resolving deadlock without detection and recovery. Since creating a general resource allocation graph uses an algorithm of high annotation, many operating systems do not use any mechanism for deadlock resolution, and Windows, mind you, is one of them. They place the burden of deadlock resolution on the shoulders of the user. When nothing happens in the system for a seemingly long time, the operator simply begins destroying processes until the system appears to be operational again. Does this sound familiar to you? Have you ever seen that your system has not been doing anything for a long time? Then you pressed Control, Alternate, and Delete together, called the task manager, and started killing processes on a whim, not knowing killing which one would work, but you kept killing processes until the system started to respond. That was you resolving a deadlock without any algorithm. The system was not preventing a deadlock, the system was not avoiding a deadlock, and the system was not even detecting a deadlock. But a deadlock had occurred, and you, as the user or the operator, were trying to find your way out of it. The brute force approach is to reboot the entire machine, thus destroying all processes, even though only the processes involved in the deadlock needed to release their resources. This should also sound familiar to you, because sometimes when the machine is not doing anything, then the last thing that we think about is press the restart button. And that is the brute force approach that we are talking of here. Now we continue our discussion on deadlocks, but move to our first book, Book 1, William Stallings, Chapter 6. We are now going to look at the classical synchronization problem for deadlocks, known as the dining philosopher's problem. So, this is the story. Five philosophers live in a house where a table is laid for them. The life of each philosopher consists principally of thinking and eating. Through years of thought, all the philosophers had agreed that the only food that contributed to their thinking efforts was spaghetti. Due to a lack of manual skill, each philosopher requires two forks to eat spaghetti. The eating arrangements are simple. A round table on which is set a large serving bowl of spaghetti, five plates, one for each philosopher, and five forks. A philosopher wishing to eat goes to his or her assigned place at the table and, using the two forks on either side of the plate, takes and eats some spaghetti. Devise an algorithm that will allow the philosophers to eat. The algorithm must implement mutual exclusion, that is, no two philosophers can use the same fork at the same time, while avoiding deadlock and starvation. Importance of the problem. This problem may not seem important or relevant. However, it does illustrate basic problems in deadlock and starvation. Attempts to develop its solutions reveal many of the difficulties in concurrent programming. In addition, the dining philosopher's problem can be seen as a representative of problems dealing with the coordination of shared resources, which may occur when an application includes concurrent threads of execution. Remember, in threads, we said that whenever a thread asks for a resource, the resource is placed in the process's address space. So, this means that that resource is being shared by all the threads of that process. So, this is a situation where you have a resource shared among many entities. Accordingly, this problem is a standard test case for evaluating approaches to synchronization. Here I present to you the first solution to the dining philosopher's problem. The solution has been implemented using semaphores. Take a look at the global variables. We have created an array of semaphores. This array has 5 elements from fork 0 to fork 4. All of the elements of the array have been initialized to 1. An integer I has also been shown as part of the global variables, but it serves no purpose and you can strike it out of the code. If you look at the main program, it simply begins all the 5 philosophers together using the begin construct. So it is fairly simple. Now let us concentrate on the philosopher code. The philosopher code consists of a while true loop. The philosopher mostly thinks. Then it does a wait for fork I. And if it can get this fork, then it moves to the second line of code where it does a wait for fork I plus 1 mod 5. This is the fork on the other side of the philosopher. If it can get this fork, then it moves to the next line of code where it eats, and it can eat as long as it likes. After it has done eating, it puts down the fork that it took up later. So it signals fork I plus 1 mod 5 first. Then it puts down the first fork that it took up. It signals fork I. And then it loops back in the while true loop. Things that you gather from this code are: each philosopher picks up first the fork on the left and then the fork on the right. After the philosopher is finished eating, the two forks are replaced on the table. Now let us do a parallel trace of the same code that we just saw. When we start, all semaphores are 1. What I'm trying to say is fork 0, fork 1, fork 2, fork 3, fork 4. All of them are 1. Let us suppose that philosopher 0 comes in and starts thinking. Then philosopher 1 comes in and starts thinking. Then philosopher 2 comes in and starts thinking. Then philosopher 3 comes in and starts thinking. Then philosopher 4 comes in and starts thinking. All of the philosophers are thinking now. Then philosopher 0 waits on fork 0. It does not block. Fork 0 becomes 0. Remember, it was 1 initially. Then philosopher 1 waits on fork 1, does not block, and fork 1 becomes 0. Then philosopher 2 waits on fork 2, does not block, fork 2 becomes 0. Then philosopher 3 waits on fork 3, does not block, and fork 3 becomes 0. Then philosopher 4 waits on fork 4, does not block, and fork 4 becomes 0. So all of our philosophers came in, started thinking, and then all of our philosophers tried to grab the first fork and they got their first forks. Now, philosopher 0 waits on fork 1 but blocks because fork 1 has become -1. If you look back at the trace, fork 1 has been picked up already by philosopher 1. Philosopher 1 waits on fork 2, blocks on it as fork 2 is -1. Who has fork 2 right now? Philosopher 2. Then philosopher 2 waits on fork 3 but blocks because fork 3 becomes -1. Who has fork 3 right now? Philosopher 3. Then philosopher 3 waits on fork 4 and blocks. Forks 4 becomes -1. Who has fork 4? Philosopher 4. Then philosopher 4 waits on fork 0. How did that happen? 4 plus 1 is 5. Mod of 5 will give you 0. So philosopher 4 waits on fork 0 and blocks, and fork 0 becomes -1. So who has fork 0? Philosopher 0. At the end of this trace, all of our philosophers are blocked waiting to get the second fork. Do you think they will ever be unblocked? This solution, alas, leads to deadlock. If all the philosophers are hungry at the same time, they all sit down, they all pick up the fork on their left, and they all reach out for the other fork, they will not find it there. In this undignified position, all philosophers starve. Each philosopher will not leave the fork he already has, and he will not eat because he does not have the other fork. So each philosopher will be blocked, waiting for the other philosopher. Techniques to overcome the risk of deadlock. We could buy 5 additional forks, a more sanitary and COVID-19 friendly solution. Don't you think? We could teach the philosophers to eat spaghetti with just one fork. Yes, that could be done. As another approach, we could consider adding an attendant who only allows 4 philosophers at a time into the dining room. With at most 4 seated philosophers, at least one philosopher will have access to 2 forks. This is the second solution to the dining philosopher's problem. It is improved to combat deadlock. But first, I need to talk to you about a few corrections in the code. In the book, semaphore room is initialized in the wrong way. This is how we initialize an array with the same value at all indices. But semaphore room is a single variable and not an array. The correct way to initialize a semaphore is this. Here we are initializing a single variable. Remove the curly brackets. Also strike out the global integer I because it has no function in the code. Again, we have an array of semaphores from fork 0 to fork 4, and all of these elements in this array have been initialized to 1. This is all about the global variables. If you look at the main program is the same too. We are beginning all our philosophers using the par begin construct at the same time. Now look at the philosopher code. The philosopher code is similar to the one we've seen. It starts with a while true loop and then the philosopher thinks. But now we are considering that the philosopher thinks outside the dining room. So when the philosopher has done thinking and it feels hungry, then it tries to get into the dining room. How does it do that? It waits on the semaphore room. Either it can move past the semaphore or it can get blocked on the semaphore. If it can move past the semaphore, then it goes and seats itself on the dining table in its chair and waits on the first fork or fork I. If it gets the first fork, then it waits for the second fork, fork I plus 1 mod 5. If it gets the second fork, then it starts eating. It can eat as long as it likes. When it is done eating, it puts down the second fork first. So it signals fork I plus 1 mod 5. Then it puts down the first fork it took up. So it signals fork I. Once the philosopher has done eating, there is no reason for the philosopher to stay in the dining room. So the attendant asks the philosopher to leave the dining room, and the philosopher does so by signaling at the room semaphore, after which it loops back in the while true loop. We are now doing a parallel trace of the second solution. When we begin, all folks are 1 and the room semaphore is 4. Suppose that philosopher number 0 starts thinking. Then philosopher number 1 starts thinking. Then philosopher number 2 starts thinking. Then philosopher number 3 starts thinking. Then philosopher number 4 starts thinking. So now all our philosophers are thinking, standing or sitting outside the dining room. Then philosopher 0 becomes hungry. So it waits on room, does not block, room becomes 3. Then philosopher 1 becomes hungry, waits on room, does not block, room becomes 2. Then philosopher 2 becomes hungry, waits on room, does not block, room becomes 1. Then philosopher 3 becomes hungry, waits on room, does not block, room becomes 0. Then philosopher 4 becomes hungry, waits on room, but the attendant tells him to stay outside. So it blocks on room, room goes to -1. Now the first 4 philosophers are inside the dining room and seated. The fifth philosopher is standing outside. Suppose that philosopher number 0 waits on folk 0. It does not block. Folk 0 becomes 0. Then philosopher 1 waits on folk 1, does not block. Folk 1 becomes 0. Then philosopher number 2 waits on folk 2, does not block. Folk 2 becomes 0. Then philosopher number 3 waits on folk 3, does not block. Folk 3 becomes 0. All the seated philosophers have now taken their first fork in their hands. Continuing the trace, fork 0, fork 1, fork 2, fork 3 are 0, fork 4 is 1. The room semaphore is -1 and philosopher number 4 is blocked on it. Philosopher 0 waits on fork 1 but blocks on fork 1 and fork 1 becomes -1. Philosopher 1 waits on fork 2 but blocks on fork 2 and fork 2 becomes -1. Philosopher 2 waits on fork 3, blocks on fork 3, fork 3 becomes -1. Philosopher 3 waits on fork 4, does not block, and fork 4 becomes 0. Now philosopher number 3 starts eating. When it has finished eating, it puts down its second fork. So it signals fork 4 and fork 4 becomes 1. Then it signals fork 3. Fork 3 becomes 0 and philosopher number 2, which was blocked on fork 3, unblocks. After it unblocks, philosopher number 2 goes on to its next line of code and starts eating. Philosopher number 3 leaves by signaling on room. Room becomes 0 and philosopher number 4 unblocks. Philosopher number 4 waits on fork 4, does not block, fork 4 becomes 0. Then it waits on fork 0, which is 4 plus 1 mod 5, and blocks on fork 0. Fork 0 becomes -1. Meanwhile, philosopher number 2 was eating. When it has finished eating, it signals fork 3. Fork 3 becomes 1. Then it signals fork 2. Fork 2 becomes 0 and philosopher number 1 unblocks. And finally, philosopher number 2 leaves. You can continue the trace and you will be able to see that each of the philosophers gets to eat and there is no deadlock. Points about the improved solution. In this solution, we do not let the fifth philosopher come into the room when four are already inside. This solution is free from deadlock and starvation. Lessons from the lecture. We explored consumable resource graph models. We learned how to detect deadlock for consumable resources. And then we learned how to detect deadlock for general resource systems. We explored recovery mechanisms. And then we explored the solution to the dining philosopher's problem. Dear students, please do all the examples that I have done in this lecture by hand on paper so that you understand how I did those things and what assumptions I made and what were my limitations. Read the book, note your questions, and email me your suggestions. This is the end of the chapter Deadlocks. I'll see you with a new chapter in the next lectures. Take care. Allah Hafiz.